Okay. It's loading. Yeah. Okay. So welcome. Hope you had a nice break. Welcome to lecture 10 on linked data. This is also the last lecture of this type of the course, and then we're going to pass to projects. Well, we're going to dedicate the rest of the course to projects. So linked data. What have we left to discuss? So we've already discussed in the semantic web architecture, we've already discussed data, which is RDF, logic, which is RDFS and OWL, queries, which is Sparkle, and the last time we also spoke about validation on the data level. Yeah, so there's one part that's missing that we've not really seen that much of. Maybe at times we've seen a little bit of it, but it's the web. So if we want to create a web of data, the question is, how do we put all of this stuff on the web effectively? So how do we use RDFS, OWL, and Sparkle to build a web of data? So in a lot of the labs, we use this EX example namespace, which is sort of strange. So today we're going to talk a little bit more about why we use IRIs and why we have namespaces and so forth. So what we're missing from this picture, the missing link, we're missing links. Yeah. So what are we missing from building a web of data? We need to somehow interlink these documents. Yeah. We need to interlink the data. We need to interlink the ontologies. So we're missing links. So the question then is, how can we add links to this picture? So where do we add the links? How do we add the links and so forth? The answer to this is pretty simple with RDF. We've already added links. We've already been adding links all of the time. So we've been using IRIs as identifiers for elements. Yeah. So every IRI here effectively can be a link. Yeah, we could click on that and we could go to a web page that describes that in more detail. For example, if we see the citrus thing in our data, we can say, what is citrus? I don't know, I want to get some more data about that. Then the idea is that we can click on that and it will give us data in RDF about what the citrus thing is. Yeah, it could give us some definitions, for example. So we don't need to explicitly add links because any IRI in our data could be a link. It could be something that we click on and find out more information, not just for the nodes or the entities, but also the relations. Yeah, we could click on, for example, a property to see what it means, how it's defined, what semantics it has. So this was one of the main ideas behind linked data. It seems obvious now, because even since the very start of RDF, we use URIs or some sort of web identifiers to identify things. Prior to linked data, what was happening was that people were publishing RDF on the web, but they were creating a very large file and then zipping it and then uploading it to their homepage and then pointing to that as if it were an XML or a JSON. Well, there wasn't JSON at that time, but they were just uploading these monolithic data sets, which were very cool and very useful, but there was no web. It was just this isolated islands of data that couldn't be automatically accessed. Yeah? So there was lots of dumps of RDF, and there were very large OWL ontologies, which were difficult to reuse. There was no reuse of IRIs, there was no links, there was no web. It's just another data format, and that's not really very useful. Yeah. So you could just use XML at that time or something like JSON and have a very similar effect. So linked data was this idea essentially of what we discussed, this idea of making the IRIs in RDF clickable. So when you click on it, you go to some other web document and you get RDF data about that thing. Yeah. If we think about all of the web doing this, then we have this web of data. Yeah. So in 2006, the linked data design issues document was published. This was by Tim Berners-Lee, the inventor of the web, who had a nice mug that we'll talk about in more detail later. But essentially, it discussed this idea that the semantic web isn't just about putting data on the web, just publishing a zip of an RDF file somewhere on your homepage and linking to it. Yeah, it really should enable linked data on the web, or a web of data. Yeah? So like the web of hypertext, you have links between documents. Now the idea is that you have links between data. Yeah. And if somebody wants to point to some data, they can reuse the IRI. So if there's a very large data set and somebody wants to point to some element of that data set, they can use the IRI that identifies that element in the data set. So the key idea is to use IRIs or URIs in this time. IRIs came along later to identify the elements that we want to discuss, and then to make those IRIs look upable or dereferenceable using HTTP, the web. So the four principles: use URIs or IRIs as names for things, use HTTP URIs so people can look up those names, when somebody looks up an IRI or URI, provide useful information using the standards such as RDF, RDFS, Sparkle, OWL, whatever it might be, and include links to other URIs so that they can discover more things. Yeah, so these are the basic principles. This was quite a powerful idea, and it led to quite a big move forward towards using RDF on the web. Yeah, so this recaptured the original idea of RDF, which wasn't just publishing dumps in RDF format, but rather creating a web of data. So we'll have a look at some examples. These examples are based on some planets that were discovered with Chilean telescopes in the north of Chile in the Atacama Desert, which are the TRAPPIST system. So there was a star discovered with 6 or 7 planets orbiting it. So on Wikidata, we have this TRAPPIST-1 entity. So it is a ultra-cooled dwarf star. And here we have some information, we have some labels, we have some instance of, and we've already seen a bit of Wikidata in the second Sparkle lab. So how does this work? How is this viewed as linked data? Well, if we go back here, we see that all of the elements are links, effectively. We can click on them and we can go and get some more data about that thing, right? So if we wanted some more data about red dwarf, we just click on red dwarf, and that gives us some data about what that thing is. Yeah, so all of the data set is interlinked. Yeah, this is the key idea behind linked data. So how does this work? We have some sort of graph here, which is an RDF, and we have some location on the web that says ex.org/data/TRAPPIST1. This is the web document somehow that if we look this up, we get returned this RDF graph here. Yep. So we have this RDF graph about TRAPPIST1 in the TRAPPIST1 document. Let's say we want to see TRAPPIST1b. Well, we can click on TRAPPIST1b, and we can get back some other web document, yeah, which is now ex.org/data/TRAPPIST1b. And in this document, we get back an RDF graph that focuses on TRAPPIST1b. Yeah. If we want to look at TRAPPIST1c, we do the same thing. We get to a different web document that has an RDF graph that focuses on TRAPPIST1c. Yeah, if we want to go then continue to look at extrasolar planet or even some properties like instance, we can click on those and get some data back about those. Yeah. So we create this web of data. Yeah, this linked data set. So this is combining somehow the ideas of the web and publishing data. So what's the benefit of all of this? The benefit of all of this is that if we use RDF, in theory at least, we should be able to just take the union of all these graphs, very fancy animation, and then we have a global view over all of the data on the web. Yeah. So we get this view that we can then query using Sparkle, for example, composed of the content of different documents on the web. Yeah. This example focuses on one website. It's sort of Wikidata, but we could consider doing this over the entire web, across website as well. And this is the core idea of linked data. Yeah? So we have different elements of data described in different places. So after we've done this, yeah, we can take our graph. We can take our graph collected from lots of different web documents, for example, index it in a Sparkle endpoint, and then run some queries over it to query the union of the data, all of the data available in these places. So this is the core idea of linked data. Yeah. So we have our IRIs and our data, but these IRIs also serve as links to find on the web some more data about those elements that are identified. So this is linked data. So the question then is, how can we implement these links called dereferencing? Yeah, so how can we implement, in a technical sense, how can we implement this thing here where we click on this and we get to this web locations web document here? Yeah. Any ideas? So we have somehow an identifier, which is an IRI for our element. And when we click on that, we need to get to this document here. Any ideas how we do that? We call this dereferencing. So we'll have a look at 3 different options. Yep. And this was the subject, although it seems kind of trivial or strange somehow, this was a topic of major debate in the community. People really fought over this. Yeah, this was almost like a civil war in the semantic web community, how to organize this. So there are 3 options, and people argue for all 3. There's one for which there's a very strong technical argument against, but we'll see. Okay. So implementing linked data. So the three recipes that we have, there are three ways we could implement this dereferencing. One is the URL recipe, one is the hash recipe, and one is the slash recipe. So we'll look at each of the three now. So the URL recipe is the easiest. What do? When we use this identifier here, the identifier we use is just the same as the location of the document that describes it. Yeah. So we just take this URL here and we use that to describe this, to identify this element here. Yeah. So the identifier for the document and the identifier for the, in this case, the planet itself, they're the same. So we're done. Yeah. There's nothing else to do. So this has a couple of drawbacks. This would be quite convenient. We don't have to do anything more complex. We just use the web page here as the identifier as well for the planet. Yeah, the web page or the web document that describes this planet, we use that as the identifier for the planet too. So that's easy. So what's the problem? Can anyone foresee a potential problem?
Would be huge. The size of the link.
So this could be a very large identifier. That will happen in all the cases, but we can use some tricks to. So what will happen here in the background often with these sorts of URLs is there will be a web server that will interpret it and then convert it into maybe a query in a database or something. Yeah, so we can use some tricks to make the URL short. Any other ideas of potential problems? Yeah.
But identifiers have to be unique and things that are named the same have to be different sometimes.
So yeah, all of the identifiers have to be unique, and that's the key problem. Yeah. So, but the second part was the
things that are called the same have to be different sometimes.
Yeah. So in this case, if we had something else called TRAPPIST1C, then we would need to be very careful that we don't assign the same URL. Yeah. So we could do we could still use this recipe with something like Wikidata, where we do Q1, 2, 3, 4, and then we assume that things are the same. But the first part is the key part. That identifier should be unique. Yeah. Which means that we should use one identifier to identify one thing. Yeah. And the problem here is that we're using one identifier to identify two things. We're using it to identify the planet, and we're using it to identify the document. Yeah. And that's not great. So what is the problem with this? Well, if we want to, in this case, we have some RDF graph or some RDF data here that describes clearly the planet, saying its parent is this TRAPPIST-1 star and it's in the constellation Aquarius. Yep. So that's all fine. And then we take another RDF document here and we say that, okay, this document TRAPPIST-1C, now we're describing the document itself, was last updated in 2018 and its creator was Jane Smith and John Smith. Yeah. Now, if we take the merge of this data, if we take the union of this data, what do we end up with? We end up with TRAPPIST-1C, parent TRAPPIST-1, constellation Aquarius, TRAPPIST-1C, the planet / document was updated in 2018. And we can interpret that the thing that has parent TRAPPIST-1 was created by Jane Smith and John Smith. Yeah, that they somehow created the planet. Yeah. So it's very natural to use the document URL, the location of the document, as the identifier for the document too. Yeah, so we don't want to, we want to reserve the URL of the document, the location to identify the document itself and not the thing that the document describes. So document URL should only identify documents. Yeah. So it relates to this. You've probably seen this before. This painting by René Magritte, I guess. Apologies for my pronunciation. Ceci n'est pas une pipe, which says this is not a pipe. And this was a famous artwork. So the idea is you can't take this pipe, you can't fill it, you can't smoke it. It's an image of a pipe. Yeah. So it's a difference between the representation itself and what it represents. Yeah, so the document is not the thing that it describes, is the point. So this is very much an argument against the URL recipe. Some people still argue for the URL recipe. Facebook in general have argued that this is fine. Nobody cares. Just use the URL, just use the web page for the thing. Nobody cares. This is not a problem, but most people would argue that this is a problem. Yeah. We don't really want to, it's very easy, very useful. You just go to a web page about something, you copy the URL, and then that's the identifier you use. But that's not ideal for the reasons we saw. It's not well founded. Okay, so the second option is the hash recipe. So the idea is we're going to use something called a fragment identifier to identify things. And this is conceptually pretty straightforward. Okay, so apologies. The first recipe we're going to rule out. We're only going to use the URL recipe in the case of documents, nothing else. We can still use the URL recipe if we want to describe a document, but not the thing the document describes. So the second recipe, the hash recipe, we're going to use something called a fragment identifier to identify things. Do you know what a fragment identifier is? No? It's basically the part that comes after a hash in a URL. Yeah, so if you see URLs with a hash and then some fragment, often if you click on that, if you're on the web, it will bring you to a subsection of the web page. Yeah. These fragment identifiers, the part that comes after the hash, is completely transparent or should be transparent to the server. It's only client side. So what happens is you enter that into your browser with the hash. Your browser takes that, it just drops the hash, it retrieves the document, and then when the document is loaded, it uses the hash to jump to the section if there is such a section in the web page. Yeah, it doesn't send that to the server because the server doesn't care. Yeah. So these are called fragment identifiers. So the idea is we can distinguish the string that identifies the planet from the string that identifies the document by adding, for example, hash this or something similar. In that way, if we add these fragment identifiers, we have one string which identifies the planet and we have another string that identifies the document. But still, when we click on this, we'll still be going to the same document location to retrieve the document. Yeah, so we have two different identifiers, but just one location. So in this case, we say that this IRI or URL here identifies the document. We say URL when it's actually a location, it gives us directly the document. And we have this IRI here, which has this fragment identifier, this hash this, which separates or distinguishes this identifier of the planet from the identifier for the document. So still, if we look this up, we'll still get the original document. So that's the second recipe. Yeah. So on the HTTP level, what happens? We do a HTTP get on this URL. We put this in gray because the client doesn't need to send this to the server. Sometimes they will anyways, but they don't need to. The server returns the RDF data. Yeah. So with the 200, okay, this means, yeah, okay, this is the document you want. Here you go. Yeah. Okay. So hash recipe is recommended. In general, it's still recommended for use. There's no major issues with the hash recipe. It's a recommended way of publishing linked data. And the third recipe and the second one that is recommended is the slash recipe. Yeah. So what is the slash recipe? So we're going to use redirects, and we're going to use a special type of redirect to point from the identifier for the planet or the star or the entity to the web page that describes it. So this is the more complex recipe. So what we have here is we have some identifier, and in this case we have example.org/entity/trappist1b. So it's no longer data, it's entity. And here we have the same thing, example.org/entity/trappist1c. So what happens is essentially these get redirected, these URLs get redirected with a special redirect to the document that describes them. So essentially the IRIs that identify the entities can be completely different from the locations of the document. And we use a redirect to map from one to the other. What's the special redirect we use? We use something called a 303 redirect. So yeah, we have here our slash recipe where we have the IRI that identifies the URL or IRI or URI. This is all three. That identifies the document itself, the location of the document that describes the planet. And here is the identifier for the planet. And we see that this identifier can be completely different from the location of the document. Yeah, it doesn't have to be a prefix like in the case of hash recipe. So this identifies the planet, and then we look it up and it redirects to the document. So we'll have a look at how this works. We do a get, and on the identifier for the planet, we get a special redirect called 303C other. What other redirects are there? Does anyone know? What's a 301 redirect? 302? So a 301, I hope I don't get this wrong. 301 is a permanent redirect. It says this website has moved, and you should, anytime someone asks for this website, you should just point them directly to this other website. So it means if you see this in future, just skip the redirect and go straight to the new location. Yeah. 302 is a temporary redirect. It says for the moment we're redirecting to this website but that might change in future. So don't jump the redirect in future. Okay. And then 303 is this C other. It says essentially this 303 code. What it says is I can't return what you're looking for because I'm a computer on the web and you're asking for a planet, but you can find some other information about what you're asking for here. Yeah. So a 303 is basically interpreted as you're asking for something that's not something I can return, but have a look at this other thing here. Yeah. So this is a good semantics for what we want in linked data, where the computer can't return the planet, right? It can't get this thing that is identified by this this identifier here, but it can point to some related data using 303. So this just sends, this only sends the location of the document about this. So then the client has to do another get on the location returned from the redirect. And then finally, the server will return the RDF data or the data about the planet to the client. Yeah. So this is the slash recipe. So this is also recommended for use in linked data. These two are the ones that are recommended, and this one's recommended just for documents. If what you're describing is really a document on the web. So hash versus slash. We see the two main recipes here. Which do you think is better, hash or slash? Any arguments for one or hash? Why hash?
Because the directory still needs to load other resources in order to get to where you want to go.
Yeah, so in this case, we have essentially two requests, right? Whereas here we only have one request. So we have in half the number of requests, we can implement this. Still, Wikidata, for example, uses the slash recipe, and so does DBpedia and various other large websites. Yeah. Why do they use the slash recipe? One thing that's nice for them, in this case here, you have no choice. Once you set the identifier for your entity, the document has to be in that location. It has to be in the location before the hash. You can't move it. Yeah. If you move it, you'd have to rename the entity to make it dereferenceable again. Whereas in this case, we can define whatever we want here within the web server we can control, and then we can move that around. We can have a different backend implementation that retrieves the data and rewrite the URL to something else. Yeah. So there's a bit more flexibility here. The other issue is what happens if we have, for example, how would this work with Wikidata, right? So we would have wikidata.org/data/entities or something, and then we'd have a hash for each queue. But that would mean that all those queues would go to the same document. So we would have to have this massive document that describes all of the entities that we described. Now there is a trick. We don't necessarily need to do that. We can implement it in this way and put the entity identifier here. But that's seen as somehow a little bit messy. So the main benefit of the slash recipe is that we decouple the IRI from the location of the document that describes it. So that gives us a little bit more flexibility in how we publish the data. So hash has half the number of requests, but slash decouples the document URLs from the entity IRIs. Yeah, so there's still a lot of debate about this. Yeah, some people are really fans of hash recipe and some people are really fans of slash recipe. Both of these recipes, again, are important to be able to have two different identifiers, one for the document and one for the thing the document describes. Yeah. So another important aspect of linked data is how, in general, we're talking about how to use the web architecture to publish data, yeah, in RDF format. So another important aspect is something called content negotiation. Have you seen content negotiation on the web before? No? So when you do a request via HTTP for a certain resource, sometimes the resource might be available in different formats. For example, it might be a video. You might have the video available in an MP4 format, in a WMV format, in a MOV format, in different, or MKV, whatever it might be. So the idea is that when you send a request via HTTP, that's just for videos. We could also have data that's in JSON format or XML format or CSV format. It might be the same data. Yeah. So when we send a HTTP request, we send also an accept header, and this says this is the format I would like to get. Yeah. So you're negotiating with the server to say this is my preferred format. In this case, because the client is perhaps a bit crazy, they're asking for application RDF XML, which is the most horrible syntax out there. But they're asking for this, and they request some IRI that identifies the planet, and then the server, based on the accept, can return a 200 OK the location that it returns. It can return RDF data effectively, directly. So this can be used to negotiate with the server what format is returned. Of course, the server might not have all of the formats. If you look at your browser, what your browser will send is an accept header where it will have text/HTML 0.8. It will add some preference score to it, and then it'll say application XHTML 0.2, text CSV, text. It'll just have a long list of different formats that it will accept. Yeah, preferably HTML, but you can override that to ask for RDF data. So in this case, we can also do the same thing. We apply the same, we're asking for the same document, but we say we want the text HTML version, and this time the server will return the HTML version. Yeah. So this is nice because this means that we can get a human readable version of a document, or we can get an RDF version of some data. Yeah. So this is commonly implemented. So we can ask for what kind of format we want to describe this entity. If it's a human looking at it, we can ask for an HTML version. If it's a machine or maybe somebody working with RDF data, we can require an RDF format. So we can also choose different RDF formats. We could ask for a turtle, we could ask for RDFA, we could have a list of preferences with scores of what we'd like to be able to process. With the slash recipe briefly, we have the same except here, but this time we have a slash recipe identifier. Then we have a 303C other, we do a get, and then we do the OK. So in the 303C other, the redirect will redirect to a particular URL based on the content negotiation that was asked for. In this case, an XML document, for example. And at the end, we get our RDF data. And this is the case for text HTML. We see that the difference here is if we ask for HTML instead of RDF XML, in the redirect here will be redirected to a different location. Yep. So content negotiation is widely used for managing different types of formats. And this is all compatible with web architecture. So that's essentially linked data, the technical side. Any questions or doubts? Okay, so why is this topic interesting? I guess you can see the benefit of this because now we can put RDF data on the web and create links between different documents on the web and create ways where someone can click on some element of an RDF data and retrieve a document elsewhere that describes that, yeah? And then if we think about all of the web doing this, it forms a web of data. So where did this idea get traction? This idea has gotten traction through the what was called Linking Open Data Project, which was a group of people, when they saw the principles, they were like, okay, these principles are great, but now what? Yeah, how do we get this started? How do we get moving with linked data on the web? So they created a project called the Linking Open Data Project, a community, let's say. The main idea behind the community was that it was sort of contemporaneous with a movement, which was the open data movement. Yeah, around the same time, people were thinking, hey, we have the web, we have our governments, we have all these organizations, yeah, they have all of this data, these data available. How can we make them available for the public good? Yeah, how can we publish data and make them available for other people to use on the web? So, I mean, the common thing and the thing that many people still do is publish a PDF or a CSV or maybe now a JSON or an XML or something, right? So they were thinking about, but then people wouldn't use it because they don't understand the format. They don't know what the columns mean. They don't, it's very difficult to query. There's no unique identifiers. So people in the open data community were thinking, okay, we have these data that we think could be useful to people. We'd like to share it with people. We'd like the public to use these data for some social good. But how technically should we publish these data on the web is the question. And the linked data people were like, okay, we've got this new publishing paradigm, this new way of publishing data on the web, which is linked data, but we have no data to publish. Yeah. So where do we get the data to publish with this new paradigm to try this out? So this was the main idea of linked open data. Yeah, was to have look at open data on the web, work with people together and try to get them to publish their data as linked open data. This is the idea. To provide some technical tools, to provide technical support, to actually in some cases take data sets and publish them as linked data and so forth. In order to reach the open data community, and this was the mug we saw earlier on the Tim Berners-Lee's design issues for linked data. he proposed 5 stars of linked open data. And the idea was to have some sort of value or to have a good story to tell people who wanted to publish open data and don't care at all about RDF or linked data. Why should they do this? Yeah. We mentioned it briefly in the first class, but to go through it again, the first star basically of open data is to publish the data under an open license. This is sort of like open data, the base case. You need to not just publish your data, but you need to say that this is available under CC0, CC BY, or some other data license. Make the data machine readable. So in this case, what this means is you don't want to publish an image embedded in a PDF of a table that was hand-drawn in crayons by children. You want to have some sort of machine-readable format, some structured format like a CSV or a JSON or something that, or even an Excel spreadsheet or something that a machine could read. For example, a spreadsheet would be better than an image of a table in a PDF. Use non-proprietary formats. So we don't really want to work with proprietary formats, although I think there was somebody commented as well on this, that you can get open libraries that will parse Excel files. Still, it would be more convenient to have a non-proprietary format, such as a CSV. Then CSV file would be better than Excel, and a TSV file would be a lot better than a CSV file. I'm a much bigger fan of TSV than CSV. So separating by tab rather than column, but okay. The fourth star, and now we're getting into RDF, is to use URIs to name your stuff. So instead of having a string Santiago in your CSV file, and Santiago, what does it refer to? Does it refer to Santiago de Chile, Santiago de Cuba, Santiago de Compostela? There's various Santiagos, yeah? In this case, the idea is to use a URI or an IRI, which would come later, to identify your stuff. So what does that mean? It means now that instead of a string Santiago, I have a unique identifier, and I can click on that, and I can see, Santiago capital, Chile. This is the Santiago that's in Chile, for example. Yeah, so it provides context. So we use unambiguous identifiers that can be looked up, and then provide links to other content. This is the idea that you want to contextualize. For example, Santiago, you could just create a new IRI for your Santiago, which would be example or my data to 2 dots Santiago. Yeah, that's good, that's fine. But if you have no more data about that Santiago, it doesn't provide context. What would be even better would be to say Wikidata Santiago. Yeah, so now you point to Wikidata, and on Wikidata, you can click on that Santiago, you get to Wikidata. It wouldn't be Wikidata Santiago, it would be Wikidata Q12345, whatever. You click on that, it brings you to Wikidata. Thumb good? Oh, it's very soft. So it would bring you to Wikidata, and then from Wikidata, you get all of the contextual data about Santiago, which city it is, but also some links. Yeah, so you also get some links to other places that describe Santiago. So now your Santiago is rooted in the context of all these other data sets and all this other data available on the web. So this provides links that consumers can follow to find out more, but it also contextualizes what you're talking about. So it really grounds that this Santiago is the same as that Santiago and all these other different websites. So this is very cool. So this is the mug, linked open data mug. So is your data 5-star? So the idea of all of this, again, is not that really, it's a good narrative. I like it because it says, you know, even if you just publish your data under an open license, that's good. Yeah, it's a positive story. It's not like you have to have 5-star, otherwise you're terrible. It basically says every additional star you add here adds value to your data. So it's a nice narrative. So this was used to evangelize and to bring open data people into linked data. So again, each star is seen as improving the interoperability of data, moving from 1-star to 5-star data. Okay, any questions or doubts? Okay, so linking open data sets. Was there success? Did people, manage to convince people to publish data? The short answer is yes, they had quite a lot of success with this. So one of the key data sets at the start, we'll talk a little bit about what FOF is later. This will disappear because it's not really a data set. But it's a vocabulary, which we'll discuss a little bit later. But one of the key data sets at the core of linked data was this DBpedia data set, which is still around. It's essentially data, RDF data extracted from Wikipedia. Similar in a sense to Wikidata, except for rather than adding data manually, the data is extracted from Wikipedia. Yeah, so it's like an RDF export of Wikipedia data. So there's a bunch of, all of these bubbles here are different data sets, and these links mean that essentially the data set offers links to the data sets of the other on a different website. Yeah. So we see that we have these data sets and they're starting to get interlinked, and this was the case around 2007. Then November 2007, then there was February 2008, and then September 2008, and March 2009, and July 2009, September 2010, September 2011, 12, 13, they didn't bother updating it for a while, it was just too tedious. 2014, and then they started doing it automatically using a crawler rather than using metadata and so on, and then it continues, and there's more. So there's lots of data sets out there. So one of the key aspects to remember is that each bubble here, the size, sorry, of the bubbles as well, is roughly related to the size of the data set. So some of these bubbles have billions of triples. Yeah, so if we take the sum of all of this data connected together, then it's a lot of data out there to be used. So what kinds of data sets do we look at? If we look at each bubble, we'll look at some of the more interesting bubbles that are in this data set to give a flavor of what's in this cloud. We have this cross-domain data set, which is DBpedia, which I already mentioned. It's still widely used. It's essentially RDF data extracted from Wikipedia, from different language versions of Wikipedia as well. We also have Wikidata, of course, which is one of the bubbles. We've played around, talked a lot about Wikidata. The difference is it's not extracted from Wikipedia, or not only extracted from Wikipedia, but also it's edited by humans. This is actually quite old now. Look at the screenshot, they're up to 100 million data items. Geographic data, so you can get information from GeoNames. GeoNames publishes, is a repository of places. It's one of the oldest data sets as well that started publishing RDF and linked data. Even when I started working in this area, GeoNames was around, so much older than even DBpedia or Wikidata. So this offers IRIs to identify places, and if you look it up with content negotiation, you can get RDF data about that place. So this is called GeoNames. Linked geodata, which is a very interesting project that's quite widely used as well, is essentially, if you've heard of OpenStreetMap. I don't know if you've heard of OpenStreetMap. So OpenStreetMap aims to be an open version of Google Maps. So it's essentially an open collaborative place where people can go and edit data about different maps and what's in this location. Here's a library, this is the name of the library, and so forth. And we actually used linked geodata, if you remember, in the second Sparkle class. We did the embassies, Asian embassies close to Santiago, or in Santiago Center. Where we search for the embassies, we search for them on linked geodata, which has the RDF export built from OpenStreetMap. Yeah. So this is quite a useful resource to have. Governments. So there was a lot of excitement around 2009, 2010 towards transparency, more transparent governance. And people had this question of how should we publish the data so people can use them? Yeah. Then maybe just creating a CSV and a .zip file and publishing that somewhere is not great. So there was a lot of excitement in governments about linked data, where governments were coming out and saying, oh, we're going to start publishing linked data. This is the way we want to go. So this is the UK government linked data portal. Another one is the Spanish data portal. There's also some linked data published by the Library of Congress here. Library of Congress, Biblioteca Nacional de Congreso. No. Yeah, the Congreso, yeah, the National Library of Congress. So there's also some efforts in Chile in that direction. Life sciences. In the life sciences, you have an area that's kind of both separated and connected. So you have people who study one particular area, maybe it's diseases or protein-protein interactions or genes. And these aspects are not isolated, they're somehow connected. So what people in biomedical sciences, what they would like to do is to connect the data of different data sets. They have a massive collection of data sets. They have data sets about genes, they have data sets about diseases, they have data sets about drugs, interactions, contradictions, all these different data sets that are kind of dedicated to one topic. So there's been a major initiative for linked data to use linked data to connect these things so that if you have a disease mentioned in this data set, you use the same IRI, and if you want to find out more information, you can go to the disease dedicated data set to find out more rich information for that. So it's a way of doing data integration for biomedical resources. So this one initiative is BioTORDF. This is a little bit of a different project. This is just focused on proteins. This is a very old data set as well that's been published as RDF called UniProt. So they publish linked data where you have identifiers and you click on those identifiers and get back some data in RDF about this protein. So there's quite a lot of work in that direction too. E-commerce, one of the first initiatives in that direction was something called Good Relations, which was this idea of embedding data into your web page about the products you're selling. So rather than just have your HTML document, you would embed some RDF data into your web page to say, hey, I'm selling a radiator. It has this certain wattage. It has here's an image of it, whatever it might be that you're selling. This also became very popular later, which we'll discuss through schema.org. So this is sort of a little bit redundant now, but that idea has been taken and implemented by Google and other search engines. We have media. New York Times was big on publishing linked open data. Mainly they would publish their tags and their information about this news article is about this topic. And then you could request data to find out all the news articles about a particular topic, for example. BBC is always very innovative in terms of data. BBC, there was quite a large group of people who were working on linked data. They're working on various linked data platforms. One of them, for example, was this music platform, which was all powered by linked data. So there was RDF and a Sparkle engine in the background, and then this is just kind of a front end over that. And you could query the data used to populate the website as well. And Pokemon, Pokepedia. So that's some examples of all of these bubbles. Each of these things that we discussed here would be like one of these bubbles, and we could continue talking all day about all the different bubbles and so forth. It's to give a flavor of maybe some of the data sets out there. So this raises a question, and this has been a major challenge in some sense for the community and still an open question, is that if every data set describes data with their own vocabulary, the data sets will be very difficult to integrate and query. Yeah? So if every bubble here uses its my data namespace, and they describe the same thing. So in one data set you have, let's say DBpedia human, and in the other data set you have Wikidata person, and they use completely different vocabularies, then it's going to be very difficult to describe and to integrate and to query over unify the content of these websites. So the question is, how could we address this issue? So this was an emerging kind of topic around 2009, 2010. People saw that there was a need to work on some way to have unified vocabularies. So a push towards that was the initiative called Linked Open Vocabularies, which is actually in this case more of a system that came out of it, but people were describing various guidelines for publishing vocabularies on linked data as well. What is a vocabulary? A vocabulary is a set of terms. Yeah. So what is a set of terms in the context of linked data? It's essentially all of the properties and classes, the IRIs for them that you would use to describe something. Yeah. So on Wikidata, for example, there's a bunch of classes like Q5 is human. There's classes for country, for universities, for what have you. And you also have properties. So you could say affiliation. This person has this affiliation, is affiliated to this university. So these sorts of terms are vocabularies. And the idea of linked open vocabularies was to collect together or somehow push the reuse of vocabularies to make people know that, hey, there exists this vocabulary for this topic. If you want to describe data about this topic, you should reuse this vocabulary. And the idea would be then that we would start to get more and more data published in a decentralized way using vocabularies consistently. And that would make it a lot easier to integrate the data from different sources. If they use the same vocabulary, that's a major part of the work done. Okay. So linked open vocabularies, what we see here is a diagram of how many, so each of these is a vocabulary. This is the namespace or the commonly used local name for the vocabulary. And the size, how big the circle is how many different websites, how many different domains are using that vocabulary on the web. Yeah. So we see that the most common vocabulary used is something called DC terms, Dublin core terms. This is DCE, which is Dublin core elements. So we'll go through a couple of them and see what they describe, just to get a flavor of what these different vocabularies are. So DC terms is super popular because it describes something super common. It describes documents. So it allows you to describe when was a document published, who's the creator of the document, this sort of metadata about documents. Yeah, so this is why it's super commonly used. This is the Dublin core set. So there's also another one, which is Dublin core elements, which is sort of like a follow-up to the Dublin core terms, adding more properties and more. They don't have classes, I think, it's just properties. More properties for describing documents. So we'll skip that one. FOF describes people. So essentially it describes, I'm a person, my homepage is this, I work in this place, my name is this, these are my contact details, this is where you can find me in social media. So we're going to be using this on the lab. On Wednesday, we're going to try to create a very low-tech social network within the class using the FOF vocabulary. So you'll be looking a bit more at what properties there are in this. Friend of a friend. So we have SCOS, which is a simple knowledge organization system, which allows for, this is actually also a W3C standard. Not all of these are standards, few of them are standards, in fact, but this one is a W3C standard. It allows for describing different topics. For example, you could describe, let's say, some topics such as US Civil War as a topic, yeah? So US Civil War is a topic, and then what is a broader topic than the US Civil War? You could have US war, and then you could have US politics as a higher level topic, and then you could have the US as the highest topic. These are not the same as subclass, because being a US Civil War doesn't mean that you were an instance of US, it just means it's a broader topic, right? So this sort of taxonomy, this sort of hierarchy is called the taxonomy. It's sort of a broader, narrower taxonomy. It's like categories in Wikipedia. Yeah, that would be a classic taxonomy, although it's very circular and has lots of data issues. This would be a sort of a taxonomy. Other taxonomies would be classifications and libraries, for example, where they classify different books according to a hierarchical classification. So this is SCOS, Simple Knowledge Organization System. CC is Creative Commons. It describes licensing. So this is very useful because if you publish a data set, you should describe the terms under which people can use it. Yeah. So you can use CC for that. This allows you to specify under what license a certain data set has been published, for example. There's also some debate about this in the sense that you can't really, if you publish data, maybe it's worth talking about. Is that not so relevant to the topic of linked data? In some sense it is. Let's say you wanted to scrape a data set, and the data set was online. It was on a website. Yeah. So you wanted to scrape IMDb, or you wanted to scrape some data set, and it had no indication of license, or maybe it even said that you're not allowed to scrape the data on the web. So the question then is, what is the legality of that? So the first thing is that you have something called boilerplate agreements. So if you access a website, by accessing the website, you agree to some terms, or maybe you even click on some buttons. Yeah, they have sort of a gray legal standing. The data itself, if you take the data from a website and you start using it elsewhere, the question is, what are the legal repercussions of that? Data is not protected under copyright. Data has no expression. You can't copyright the fact that I work at the University of Chile, for example. That's not a thing you can do. You can't copyright facts. You can only copyright expressions. So what happens in the EU? So you're perfectly, if you take the data, even if you ignore all of the boilerplate agreements, as well, I'm not a lawyer, this is not legal advice, but I have to add that disclaimer. If there's no protection for data under copyright. So there are arguments to say that really this is just to make clear that people can use data that you publish. However, there are certain protections in certain jurisdictions. In Europe, what can be protected is something called a database. You can protect a whole collection of data. Yeah, so you can protect, for example, that the collection itself is an expression of something. It's an expressive form. The other thing you could protect, for example, if you were to go on IMDb and you were to extract all their data and use it for some other purpose, although they'll say you can't do that, it's not really clear why you can't do that because they can't copyright data. They could, however, copyright the structure of the data, or they could copyright whatever they say requires expression. Yeah, the expression, the way it's expressed in IMDb. A classic example would be the IMDb rating. Yeah. So IMDb rating, they could argue that they have copyright of the way that that rating is calculated and expressed. Yeah, but facts are not capturable. Anyways, that's a bit off topic. So we have Creative Commons to describe licensing. So the whole idea of copyright around data is a very gray area, even legally speaking. Schema describes everything, almost everything, not everything, but almost everything. So we have this schema.org, which we'll describe a little bit later again. This is the vocabulary that was published by Google, Yahoo, Yandex, and Microsoft, I think, in order to have a broad vocabulary that could describe all sorts of different stuff on the web, from movies to products to paintings to museums to whatever it might be. So this is used by Google, for example, to create its rich snippets. So people describe the data, the metadata about the recipes. It might be difficult to see, but we have the rating here, 4.6, 1,625 reviews, 40-minute duration, 298 calories. All of those data are described using the schema.org vocabulary. Yeah, so it has all these terms. Yeah, so within the idea then is to push and to encourage the use of common vocabularies in this linking open data landscape. Yeah, so if people want to describe people, they should use both. If people want to describe taxonomies, they should use SCOS. They shouldn't invent their own each time because that makes it much more difficult later to integrate data from different sources. Okay. So we see lots of planes. In general, the ideas are taking off. Yeah. So a lot of the concepts in the semantic web, this is sort of coming towards the conclusion of the course, and also the topic of linked data, have been taking off over time. Even though if you talk to somebody on the street and you ask them, you know, what is the semantic web or what is the web of data, they're not going to have any idea of what you're talking about. They are using it. Lots of people, lots of applications are widely used now that depend on ideas that are central to the web of data. However, we're still not seeing a fully fledged implementation or realization of a web of data. So we'll talk a little bit about that. So in terms of linked data, what sorts of applications have we seen for these data sets? Who's using these data sets and for what? And what are the key applications? What are the key successes of linked data, semantic web, web of data? So I think it was about 3 years ago, I did a survey of the community. I had to write this sort of editorial piece, which is an editorialist kind of writes some general opinion or position or vision for a journal. So I did an interview, or I did a questionnaire. I prepared a questionnaire, just a simple Google form, and then I sent it to community members and mailing lists to see what they consider to be the success stories of the semantic web in general. Yeah. So here you see the size of the text indicates how many people responded. So I normalized them a bit because sometimes there was, you know, kind of knowledge graph and knowledge graphs, for example. So I did some normalization, and then the size gives you an indication. I think there was about 200 respondents or something like that, 100, 200 respondents. So this is what the community considers to be the main successes of the semantic web, the semantic web community itself. We see schema.org was one of the major things that were answered. Yeah. So schema.org, this idea that now we'll talk a little bit later about it, but the fact that there's RDF data published in so many websites. Knowledge graphs, which I'll talk a little bit about again, which is sort of a new fancy way to describe data sets published as graphs. Wikidata is a major success story according to the community. Bioinformatics, which we didn't really discuss except for very briefly, the use of semantic web technologies in bioinformatics. I was in Germany, if you remember, maybe a month ago, and I met a guy who works in bioinformatics, and he said that basically all of the ontologies they use there are absolutely essential to a lot of the work they're doing. So they're really key resources for those communities. Ontologies in general, I don't know, maybe I was trying to classify some general stuff. We have DBpedia, there's RDF, which I don't know if that's really a success story. I mean, it's just a thing that people use. Although people could say it's been successful, I guess, I don't know. JSON-LD, which is this linked data version of JSON, which is a JSON format for RDF, which is commonly used with schema.org. Semantic search, graph databases, data integration, enterprise, linked open vocabularies, Airbnb knowledge graph. There's a bunch of stuff there, so you can have a look in more carefully at some of the smaller stuff that people have mentioned as success stories. We'll talk a little bit about some of these, some of the main ones that people have mentioned. So Wikidata, I'm a big fan of Wikidata. We see that this one's slightly less out of date, but it should still say 100 million. So Wikidata is, for me, one of the major success stories as well. I would have mentioned that myself. It has seen this very large growth in terms of the data described. It's used in a lot of different applications. It's used by Siri, Alexa. It's used by, of course, in Wikipedia to generate info boxes. It's used by also just random applications like Lufthansa uses Wikidata to describe places in its world map and so forth. We have Google Rich Snippets. Yeah, so we discussed again several times this idea that we have all these metadata for describing web pages. So my family in general have no idea what I do, and they ask, what's the semantic web? And they're not technical people at all. And I say, oh, do you know sometimes when you do a Google search, you see all the data there? That's because of stuff that or the area that we're working on. Like, oh, I know that. And then they tell everyone, oh, Aiden did that. He implemented all of this, which is not true, but I don't want to correct. So this is a very visible application that you can mention to people and say, oh, well, how do you think they get these data? This is based on RDF formats and so forth. Knowledge graphs. So we have knowledge graphs. It's the same idea as what we described, but it became very popular in 2013 because Google said, hey, we have this knowledge graph that we use for organizing all of our data. And this became a very popular idea. It's not really from the semantic web, but it applies very similar topics to what we saw in this course. So it doesn't necessarily have to be RDF. It could be a different type of graph database used, but essentially knowledge graphs are often they use RDF because it's the only standard for describing knowledge graphs with Sparkle to query them. So these have been used for personal assistants, Alexa, Siri. They're used, for example, for recommendations of where to eat by Uber. There's we have the Airbnb knowledge graph of places or activities to do. And we have, for example, an Amazon knowledge graph is used to generate recommendations of what products to buy. So it's again considered a flexible format. You can just dump a bunch of data in there and then get some connections, use connections to find recommendations for elements. So the main one, again, was the Google Knowledge Graph. This was the first one released in 2013. The really strange or interesting thing about this is that, okay, other people wanted to do something similar, but rather than calling it a knowledge network or an information graph or something else like that, they decided to go with the same name. So knowledge graph was just like a name of this product that Google had, but then other people said, hey, I have a knowledge graph too. So they decided to use the same term as Google. So where's the knowledge graph? Where can you see the knowledge graph? It's used for sort of this idea of semantic search. What's the idea of semantic search? It's the idea that you understand some meaning of what is being searched for, that it's not just keywords in a document that you look up in an inverted index in some sort of index. So in this case, when we search for Surikolo, we get here this what's called a knowledge panel, which shows that Google can recognize that what we're looking for is a writer who was born in France and so forth. I think he was born in France. Yeah, born in France, in Paris. So this is Google Knowledge Panel. We have schema.org, proposed by Yahoo, Google, Microsoft, and Yandex, which was also a pretty major success, I would say, in one sense. I mean, it's not great that these companies have so much say over the directions of the web, but at least they came together and they decided to agree on a vocabulary. So we don't have a schema.org for Google, and then you have a different data set, a different format for Yahoo, and then you have a different format for Yandex, which Yandex is the Russian, main Russian search website. So it's the Russian version of, let's say, Google or Bing. And Microsoft, you don't have a different vocabulary for Bing. They decided to come together to create this vocabulary, which it has a very broad set of terms. Yeah, so it describes museums, universities, people, products, movies, actors, handbags, whatever people might want to describe on the web. Unfortunately, it's not the universal ontology or vocabulary for this. Facebook has its own, which it calls Facebook's Open Graph. which is mainly used, the main application, and the reason why people use it is for embedding information about a web page in a Facebook post. So somebody posts a URL in Facebook, then essentially Facebook will use the open graph in order to extract details of the web page to show in the Facebook post. Yeah. So this is Facebook Open Graph, and it can also be used as well to have like a like button or to have integrated Facebook features in your website. So this is I mean, it's a nice use case, it's widely used, but it's kind of a pity that Facebook have published their own proprietary format rather than using some sort of more standardized or agreed upon format. So what is the result of all of this? I mentioned briefly at the start of the course that these formats are quite widely used. Actually, I could have updated this. This was from 21. I think there's an updated one in the first class. But we see that according to the survey, 59.5% of websites, for example, publish data in the open graph format, which is this sort of RDF-like syntax, but it's not quite RDF. They just did their own thing a little bit. Like they use the URL recipe. They don't understand the need to have a separate identifier for a document and a thing. Twitter cards, which again is a vocabulary, it's not really a format. It's similar to Open Graph in that when you tweet about a link, they want to have some metadata to like give you a nice preview of what that web page is about. JSON LD, which is pretty much an RDF, it is RDF, an RDF format. We have generic RDFA, microdata Dublin core, which again is more vocabulary than a format, and some micro formats. So here we see a mix of vocabularies and syntaxes, which is not so nice. But all of these are essentially RDF compatible. This one is directly a semantic web or RDF format, and this one, of course, obviously is as well. So we see that there's a large percentage of websites that are using or publishing structured data in these formats because of these sorts of applications. Yeah, because of search engine optimization, they have nicer looking results. They get a nicer looking preview on Facebook or on Twitter of the web page when it's published. That drives traffic to the website, and it's generally a good thing to do. So here we see some trends. We see that essentially things like JSON LD are getting more popular. Twitter cards, or now I guess they would be called X cards or something, which sounds very strange. The popularity of Open Graph continues to grow and so forth. What other success stories? There was a mention of bioinformatics, and I mentioned before the biomedical ontologies. So what we talked about so far is sort of RDF and web and so forth, but what about the OWL stuff we talked about? Yeah, we had like 3 classes on OWL. Biomedical ontologies have become very important resources in their respective communities, and there are portals. There are so many ontologies, there's like thousands of ontologies, that there's also portals for these ontologies. Yeah. So this one is based on the OBO format, which is essentially equivalent to OWL, and there probably should be more OWL ones out there. So this is these are all interoperable ontologies for the biological sciences. Sorry. Basic formal ontology, chemical entities of biological interest, human disease ontology, gene ontology, ontology for biomedical investigations, phenotype and trait ontology, plant ontology, and so forth. Yeah, so all these ontologies, they use reasoning mechanisms like we saw in order to classify or to look at the consistency of different types of definitions of diseases, plants, and biologies. There's also BioPortal, which is another collection of ontologies. And if you wanted to check it out, you can just go to BioPortal, I guess bioportal.org, if I remember, or just maybe search for it. And then we see the most important ontologies, or the most visited, are SNOMED CT, SNOMED Clinical Trials, MEDRA, I don't know what MEDRA is, CPT, I don't know either, NX Norm, and CIT, I don't know what these ontologies are, except for SNOMED CT I've heard of. So yeah, there's a lot of ontologies. In this case, there's 912 ontologies describing 12 million classes, 36,000 properties, with 111 million mappings between them. We have the linked open data scheme that we already discussed. This has been very popular in terms of getting people to structure their data, their open data that they're publishing. Linked open vocabularies in this direction has been an important initiative. And there's some emerging projects as well that are gaining interest. So again, when I was in Germany, people were talking a lot again about Solid. What is Solid? Solid is social linked data. It's a project mainly pushed by, again, Tim Berners-Lee, who is not delighted with how the web is turning out in terms of the monolithical, these websites like Facebook that can subvert elections if they want, or these massive industries like Google. So the idea of Solid is to start to return or try to return to some elements of the original vision of the web, which is to decentralize everything and give its users more control. So that rather than publishing or having these massive websites, let's say like Facebook, for example, that manages all of this personal data and so forth, the idea is that users or clients can manage their own data in something called a pod, which is like a personal data store, which would be powered using RDF and Sparkle and so forth, and linked data principles, that users store their own data and they give access to applications that want to use that data. Yeah, so it's this idea of you have your own personal store, you manage your own data, and you say who has access to that and who doesn't have access to that. So that's Solid, and that's starting to get more interest. It's starting to gather more and more momentum, let's say, for different applications. I think there's in Belgium in particular, there's various applications relating to the government and to various social security things and so forth. So that's kind of interesting. It's still not, it's one to watch, I would say, to keep an eye on. Yeah, so there's some of the success stories. Solid is one of the things I think might be very interesting to watch for future. Any questions or doubts? Okay, so we're getting into just the last part to talk about some of the open challenges. I think there should be an animation here. Yes, open research questions. So there are things that are still left to do. Yeah, so it's a research topic. Yeah, it's a postgraduate course. It's something. There's lots of things that are still up in the air, still open, that haven't entirely been solved, and there's some research still left to do on this. One issue is linked data integration. So it's all well and good having all of these data sets, but one of the key things we need, for example, is to be able to identify the same entities in different data sets. So here we have Bill Clinton on Wikipedia, we have Bill Clinton on Freebase, we have Bill Clinton mentioned on the New York Times, and we have Bill Clinton mentioned in BBC Music. So are these Bill Clintons the same? What do we think? So we have Bill Clinton office holder. That sounds like Bill Clinton we would know. Bill Clinton, we have an image. Yeah, so we could say, okay. Bill Clinton here, 415 articles. Hard to imagine another Bill Clinton, it could be. And then we have Bill Clinton in BBC Music. Is this the same guy? If we read it, actually, it is the same guy, yeah, based on the biography. But I think he was a trombonist. He played in a band at some stage, Bill Clinton. He has some musical connections. So that's him, yeah. So in general, if we want to be able to integrate data from different locations, we have to be able to distinguish which of these Bill Clintons are the same or not, yeah? So all of these Bill Clintons are the same. So to be able to integrate the data in terms of the music perspective, the descriptions in New York Times, and the more open domain descriptions in Freebase and Wikipedia, we would like to be able to know that these are the same thing. Yeah, so this is entity mapping problem, where we want to detect essentially that these are the same. How could OWL help here? It doesn't really, well, it can help in some sense if we have common vocabularies and we have definitions like inverse functional properties, or if we have keys or we have some other definitions. But in general, we could use some sort of OWL same as reasoning to be able to find out that these are the same. So this would be really the OWL same as case, where we say that the BBC identifier for Bill Clinton is the same as New York Times Bill Clinton is the same as the Freebase Bill Clinton is the same as Wikipedia Bill Clinton. Second open issue, diverse vocabularies. So here we have a bunch of data in different websites, and here we use the example prefix. So we have example 1 is Frank's profile, describes Frank and where Frank lives and that he's allergic to citrus. We have another website, example 2, which is in this case a supermarket chain, and we have some information about where it is and that it sells lemons. The lemons contain citrus. We have here a recipe website, example 3. It describes a coffee parfait recipe. What are the ingredients, how to make it? And then we have an example 4, a different recipe website, which has a grape sorbet recipe. And then we have site number 5, which describes the biology of lemons as a fruit and that it contains citrus. So here we have some data that we could use to recommend Frank some recipes, recipes that don't contain citrus and where all the ingredients are available in the local supermarket, for example. And all of these data, you can find these sorts of data on the web. There's nothing really fictitious about this. This could be a real example, right? So using these data, we could, recommend recipes and say, hey, these ones you don't have any allergies noted for these recipes. They seem to be okay, and you could get all of these products in the supermarket. Yeah. The problem towards building this sort of application, which is certainly ambitious, is diverse vocabularies. That here, if we have every website is using different vocabularies to describe similar things, it's very difficult to integrate the data afterwards, even if we can identify which elements are the same. So there is an open problem on how to integrate and write queries against linked data from different sources. So one of the big directions towards solving this is linked open vocabularies to just get people to use the same vocabularies rather than using distinct ones in every website. More on the data management side, there is the open issue of linked data access. So when you were doing your lab on Wikidata, you might have encountered timeouts sometimes. I'm not sure, maybe, yeah. So there's a question of how to do efficient queries. So this is sort of a new topic because it's similar to SQL, the problem of solving SQL queries, similar to this problem of solving Sparkle queries, modulo property paths, which are not in SQL. There's a question of how to optimize this, but so it's new because nobody in general had ever put on the web their SQL database openly online and said, here, hey, query my SQL database, send whatever SQL queries you want. And this never happens. So this thing in Sparkle is kind of a new problem, a new idea. And it's not only that, if you remember in the second Sparkle class, we did a federated query where we got one query engine to query another engine to get data back and so forth. And this could be very powerful as a platform for building a web of data where we can get answers from different websites. So what we have is essentially this idea that we have clients that have questions, and then we have these servers that have data, and some of the servers might also have questions themselves in the federated case. So we send a query to one data set that then has to query some other data set. And the question then is, how do we optimize queries? How do we do this, resolve these sorts of problems in an efficient way? How can we get all of these clients and servers to work together to solve the queries that they have in as efficient a way as possible? So we have remote, decentralized, uncoordinated environment, and we have this sort of web scale. So this is also an interesting problem. There's lots of people working on this more low-level kind of query optimization in a decentralized environment. And this is quite new. This is not the sort of setting is sort of emerging through linked data. We also have, of course, problems with linked data quality. You probably have seen this as well on Wikidata. You saw that there was answers. I think the Dreamcast query was very controversial because you all know the answers that should be there and you didn't see the ones that you're expecting. So we have problems with linked data quality. Yeah, so you can't trust everything you read on the web, and in the same sense, you can't trust everything you download or find on the web of data. Yeah. So there's work towards addressing linked data quality, towards trust and so forth. What we can do, very roughly speaking, is the exact same thing we do on the web. If we find a website that publishes RDF data and it has no links, nobody on the web links to this place, then we can say this is not a highly trusted data set. However, if we found a data set that was very central to the web, on a very central in the network, maybe a news website or something, then we can assign more trust to the data found in such locations. So I worked on something similar for my PhD a long time ago. Another issue is legacy data. So if we think about the web and all the data sets, and when you go on Kaggle or whatever, we don't find that many RDF data sets. Yeah, most people just publish their data sets in CSV or TSV or maybe JSON formats now. These would be the most common formats. And we might also get some SQL database. So most data are in legacy formats. And essentially publishing them as RDF is not that straightforward. Yeah, so there's this big step here, moving from the third to the fourth star, where we need to convert from CSV to RDF and then to linked open data. There is some work ongoing on that. I think Adriana and some of you are probably facing this in your projects. You've taken some CSV data or some tabular data or maybe JSON data. And Adriana published a forum post about some recommendations of tools you can use. So there is work towards that. It's more an issue. It's not a research issue or a question. It's more a practical question of having nice tools to do this. So there would be Sparkle Generate, Sparkle Anything, Tarkle, these sorts of stuff. We used to have a class on that, by the way. I could also publish it later if you want. It's a recommendation called RDB to RDF, but it's specific to relational databases, and it's not actually what I would recommend any longer to use. I would rather recommend to use something like Tarkle, Sparkle Anything, Sparkle Generate, something based in Sparkle for this. So in any case, there is this question of how to make it easier for people who have CSV data or data from in a relational database or whatever to export and publish data as RDF or as linked data. The biggest issue, and this was also mentioned in this survey I did, which I showed the success stories earlier, is the question of usability. Yeah. So the question of usability is a major one in that, okay, if you know Sparkle and you spend an hour at it, you can do these cool queries where you find a map of embassies around Santiago that draws data from different locations on the web. If you're not an expert on Sparkle, this is completely out of your range of possibility. Yeah. So there have been, of course, many directions. In general, people would say that obviously we're not expecting users to write Sparkle queries. There has to be applications above that will use maybe a Sparkle query in the background, but the users themselves, the main, the common user on the web is not going to be writing Sparkle queries. So we need some sort of interfaces to help non-expert users to better interact with linked data, to get more out of Wikidata, for example. And this is something I've worked on with students, so like kind of more specific interfaces for interacting with Wikidata, maybe application specific or more general, but maybe focused on a particular type of interaction. I think here as well, I gave a talk during the Semana Computina, the DCC. I gave a talk as well on how ChatGPT could potentially help with this problem. So you could use ChatGPT to generate the query. So rather than asking ChatGPT something specific, which it's quite poor at, like question answering on factual information, you could use ChatGPT to generate the Sparkle query. It works quite okay at the moment, but with some fine tuning, it could work a lot better. So you just use ChatGPT as a language interface. It generates a Sparkle query, and you run that Sparkle query against Wikidata, and that would have various benefits. So maybe I think they recorded the talk. Maybe I'll share it in case you're interested to see that. So there's lots of open questions. We don't have all the answers. That's why it's a research area. But if we could solve these problems, it would mean a major leap forward for the web, and we've all seen the impact that the web has had. Yeah, so even incremental improvements in the web can have major impact. And this is sort of looking farther into the future of the web, maybe for 20 or 30 years time, in terms of what the web could look like. And some of that stuff is already getting used and implemented as part of the core web now. It's also an area of research that's very active in Chile. Here we have the Center for Semantic Web Research. We previously had a nucleo on this. I don't think you probably recognize a lot of these faces. You probably don't recognize anymore. No, which faces do you recognize? Yeah. So Jorge Perez was also, you don't know Jorge, no? Yeah, some do. Pablo Barcelon was also a professor in the DCC, and Barbara is a professor at the DCC, but she's on sabbatical with Amazon. So we have some here. These two are from Book, from the Catholic University. So you know, that's your supervisor, right?
Yeah.
That's fine. Yeah, so he's the director of the university. Now we have a new group called the Instituto Milenio Fundamentos de los Datos, which is incorporates this group and also has a more general and focus on data. Still has a core focused on the semantic web, but has a broader focus on data and also political sciences, social sciences, communications, and so forth. So it's a much larger project. So there's a lot of people working semantic web research in Chile, including myself. I wasn't there the day that picture was taken, so. Yeah, that's it. Questions? Thoughts? Okay, so that's the last class of the last lecture like this of the course. We were quite efficient this year. I think we got through everything more or less straightforwardly. This week is Semana 12, did I say? 12. So we'll have about 2.5 weeks dedicated to projects, which will be due, I guess on week 14, I'm not sure, or week 15, the start of week 15. So we'll have some time to work on projects, but this Wednesday we'll still have a lab. We're going to have a lab on linked data. So we're going to play with creating a decentralized social network based on FOF. It will not be the fanciest social network you've seen, but it will hopefully help to illustrate the concepts of linked data. For that, it would be great if you have web hosting, if you have somewhere to upload a website. If you have Anaconda, we'll try to give you some guidelines on that. It can also be GitHub, but it's a little bit awkward in GitHub. Yeah, we'll figure it out on Wednesday. So we'll always find a solution for that. So we'll have the lab on Wednesday, and then from next week on, we're going to focus on projects. Yep.
Would be the lab